So I was thinking this morning and yesterday a bit about the topic that Dwayne and I were kind of talking about yesterday, how to maybe a little bit more easily establish like when is the amount of years exactly the amount of years we're talking about, when is it one less, when is it one more. So we're going to do a bit more of that today, so just so we're feeling more comfortable with like, okay, what is actually 1 or what is 0 or when are we doing -1, those kind of things. So we're going to be doing that today in light of, remember arithmetic growth or arithmetic decay, that's where something is growing by a certain amount or decaying by a certain amount with like an additive change. This case very same, except for now it's like multiplicative. They're multiplying by something over and over and over. We'll get into like exponential growth. This is sort of actually like thinking about an intro to investing also in some of what we'll do today. But let's first of all think about the standard geometric growth story of rabbits, right? Productive like rabbits, those kind of things. So we'll think about rabbits on the University of Victoria. Wow, somebody gets a head, nice. So in this first case, University of Victoria struggling with an out-of-control rabbit population. In 2010, there were an estimated 1,500 rabbits on the University of Victoria grounds. And if it goes up each year by 20%, now, wait a second, goes up by 20%, how would you deal with that? What's increasing by 20%? Adding what? Increasing by 20%. Would there be something you could multiply by to make a number increase by 20%? Yeah? Yeah, 1.2. It's the same as saying, find what 20% is, 0.2, and then add that to the whole, right? You could just say, take the original and add 0.2 of it, or more simply, exactly, multiply by 1.2. Very good. So this means times 1.2. So let's figure this out. Give an estimate of the rabbit population in January of 2011, 12, and 13. So if in 2010 there were 1,500, okay, 1,500 times 1.2, so 1,800. Hello, welcome. Final exam review package right here. Okay, 1,800 times 1.2, 2160. Oh, this next one. Okay, and 2160 times 1.2. 2592. Okay, so how could I prove that this is geometric? What's, by definition of geometric sequence, what are we talking about again? How do they increase? Yeah? Multiplication is how to prove it. What will show that it's geometric? What can I do? Ratio, yeah, nice. So we can say like R is equal to, let's say the second one, 1,800 over 1,500. That should be equal to the ratio comparing the third one, 2160 over 1,800. And let's check, is that true? Well, in this case, 1.2. In this case, 1.2. Well, it better be, because that's what I multiplied them both by. 1.2. Okay, now, here's the thing that I was kind of hinting at, that Dwayne and I were talking about. How do you figure out which term is which? So let's just think for a minute. If this started in 2010, so now we're wondering 2025. We're getting there. We're so close. 2025. Which term in the sequence? So if A, we're calling this here A, or T1, then which term would be 2025? So 25 minus 10 is 15. Was it any term 15, or how would you figure that out? I actually thought, in my head, this is how I set this up when I was thinking of it. And maybe this is helpful. I thought, well, what I want to know is, I want to know, like, the amount minus 1, right? If term 1 is A, is, that's term 1. Let's figure out, like, what the thing is minus that 1. And that will be the same as the relationship between 2025 and 2010. Right, so the term number minus 1 should be the same as 2025 minus 2010. So 15 should be the same as x minus 1. So x should be term number 16. Term number 16, so T16, I guess we could say. And if we think about this, this does sort of make sense. In 2010, that's term 1. 2011, that's term 2. 2012, that's term 3. Term 4. Going forward, you can extrapolate and see, oh yeah, 2025 is term 16. not 1015, right? Now here's the funny thing. Exponential growth formula, or geometric growth. What's the setup for our formula we were doing yesterday? C to the n equals a times r to what power?
N minus 1.
Oh yeah, n minus 1. So this is the funny thing here. N minus 1, right? I said x, or I guess I should have said n. So how do we solve this? Well, n minus 1 ends up being, we need to get here, right? So a as 1500 times r as 1.2 to the power of 16 minus 1. Yeah. So value 1500 times 1.2 power 15. Oh, I almost put 155. Funny, I got a very strange answer. I had negative. I shouldn't have put minus times. Yeah, there you go. So what would be the rat population? What'd you guys get? It's going to be really big, isn't it? It was something times 10 to the power 15. Did you get 2.8, 1, 3, dot, dot, dot. E 15, is that what your difference is? Oh, no, sorry. Sorry, I see the issue. I have an issue, you don't, we're all good. No wonder this is different from the answer I got earlier. I put in power of 155. Power of 155 is very different. Ah, there we go, that makes more sense. Sorry guys, I was leading you on a wild rabbit chase. That look better?
Yeah.
So what would you estimate the rat population would be? I don't think that half rabbit will quite make it here. I only like half rabbits, on a plate, not in real life. So we'll say, in this case, now this is silly, it doesn't really matter, but in this case I know 0.5 would tell us to round up, but you don't take a part of a rabbit and say there's now an extra rabbit, so we have not yet got to the 23,111th rabbit, so we haven't got that one yet. Their parents are in the process of making it or something like that.
Wow.
Well, you never thought you were going to get a sex ed lesson in F20F1 day. For real. Okay, so what was the growth factor? Growth factor was 1.2, and the more tricky part is just figuring out what the n value is, right? What the n value is and how that relates. Now, similarly, and actually the same sort of math is when we have geometric decay situation. So that's where you're decreasing by some multiplicative amount. You'll notice at the bottom, down here, geometric growth between 0 and 1 is often called decay. So what that means is that you're getting smaller, but not by a constant amount, but by a multiplying amount. So for example, if I take, this is actually what's happened to my amount of points scored in my men's league hockey in the last few years. It's a very important thing. You take the points that I scored at 25, and you go times 0.9, and you can pretty accurately predict what will happen the next year. So now that I'm no longer 25, well, you can take that and go times 0.9, times 0.9, times 0.9, times 0.9, and you can see where this is going, right? Where we're going down. The nice thing is, I won't ever hit 0, so that's good. But let's think about this in this loan instead. You're like, okay, move on. Now, Vinny borrows $10,000. This is a very favorable situation, by the way, from his parents to buy a car. Parents lent him this money interest-free as long as he makes a payment at the end of the year. And the repayment scheme is 10% less, or he makes it so that he owes 10% less each year. And then at the end of year 8, he's just going to make a lump sum to pay off the rest. So this table, we have to think through what's happening. So he starts with $10,000, and at the end of the year, he makes a payment. So how much is owing at the end of the first year? No, at the end of the year, he makes a payment. So he makes a payment so that he owes 10% less. So we take what he had, 10 grand, and multiply it. What's 10% less? So that'd be 90%, so 0.9. So he has $9,000 owing. And this is going to be our key piece here, right? 10% less means 90% of. So if we want 10% less, it means multiply by 0.9. So then the next time, same idea. End of the second year, we need to have 10% less than this. 10% of 9,000 is 900. So he now owes 8,100. Right, and continuing on. So let's see. 8,100 times 0.9. Yeah, so 810 exactly. So 7,290. And then times 0.9. 61. And this B, we've already solved this. In fact, to do this, we had to have already solved for the common ratio. The common ratio is 0.9. The reason why the book, by the way, sets this up is if you were just doing this on your own, you may think, oh, I should do minus 10%, which is fine, it gives you the same value. But then you recognize, oh, if we subtract 10% off, it's the same as multiplying by 0.9. So now, how much does he owe at the end of the 7th year? How much does he owe at the end of the 7th year? Okay, let's just think again. So we were struggling yesterday with the n or n minus 1 and where each one happens. So at the end of the first year, he had made a payment. At the end of the second year, he had made a payment. At the end of the third year, he made a payment. So what would be like our A value here? So good thing. So maybe that was the wrong way to ask that. We could really choose either 10,000 or 9,000 as our A value, right? So if we choose 10,000 as our A value versus if we choose 9,000 as our A value, we're kind of making a choice, right? In one case, we're talking about the starting point being after he makes a payment. In one case, we're saying the starting point being before he makes a payment. And I'm cautious to give us options, but it's just worth thinking through. We're always kind of making decisions about the formulas we use and what we're doing in those formulas. So a part of what this is helping us set up is just what's the formula we're setting up doing for us. Okay, so we know that we have the value, or t to the n, or is equal to something. That's the number we're looking for. And we know we have an a value. We know we have an r value. Our r value is going to be consistent no matter what we choose. And we know we're going to have n value. Now, the choice we make with the n value is pretty important. So let's just think about, if we say, the most natural option here is that our A value is 10,000, right? That's what we started at. I think that's what makes sense to me to start as. We start at $10,000. If this is the case, it's a small enough number to think, how many times does that money have to compound in this situation? So it compounds once to get to the end of the first year, once to get to the end of the second year, so 2, 3, 4, 5, 6, 7. It compounds 7 times exactly. So the n value was sort of actually 8 there, right? N value is 8 because we actually needed to compound 7 times. So in this case, n would be 8. And you'll actually see later in the lesson us replace that n in this version of that with just x because it's the number of compounding periods. But in this case, it's if we start from kind of before this process begins, the beginning of the process, $10,000, no compounding has happened yet. We have 8 periods from then, which is to the end of the 7th year, because that whole first year is 1 period. Maybe that clarifies, maybe I'm making this more confusing for some of you. Probably both those things are true. So let's just continue on. So when we set this up, then t to the n is equal to $10,000 times 0.9 to the power of 7. 8 minus 1. To the power of 7. So he owes $4,782.97. With money, you always choose to round to the nearest hundredth, right? This nearest cent. So in this case, this is the lump sum payment that he makes at the end of the 7th year. I don't actually know why this seems like a really stupid scenario to me. I'm not sure why he's paying less each year and then has this massive lump sum. That doesn't seem realistic, but whatever. That's the situation. Vinny and his parents can do what they want. It is interesting to recognize, though, that like by year 6, he's making quite a small payment, and then he's suddenly expected to make a payment of like $5,000 the next year on his vehicle that's depreciated probably under that value. Because this is a total side tangent, which I never do, obviously. But value of a car. How does about the value of a car generally look in terms of value? What do you think the value of a $10,000 car after 8 years would be? Probably a lot less than $5,000. I think it'd be less. I mean, a car is $10,000 to start. Pardon? $3,000. Yeah, maybe. So I think his lump sum payment is probably more than the car is, and that's actually oftentimes when people default to stuff like that. Is if you have a mortgage that's worth more than the value of the house, with that you end up in a big pickle if if your mortgage is secured against the house itself, because that was what happened in the big financial crisis recently. So. Okay, why don't we do the key part here of like the setting up growth factors here. If you can do this, this kind of tells you that at least at its core, you're going to be able to set up situations like this, geometric growth and decay. So what's the factor of growth of inflation? If inflation, or the way your dollar is related, is increasing by 3.5% per year, what would be the growth factor there? Good, 1.035. How did you get that? Good. So let's first of all think about what would be if the economy is staying exactly flat. What percentage would it be compared to last year? Let's say I have $100 and compare that with an exactly flat economy. What's my $100 worth next year? Still $100. Right? It's a flat economy, still $100. There's been the value is equal to 100% of last year. Nothing has changed. It's not that it's grown by 100%, but it's equal to 100% of last year's money. What about if you have an inflation rate of, say, 10%? Well, 10% increase in the cost of something makes it so that it's like 110% of the cost of last year. In this case, inflation rate of 3.5% is saying it's like the decimal 0.035 times more than it was last year. So if you're thinking of this like the way you learned Math 7, you take, but let's do it more simple. GST rate. GST rate, what does that add to the cost of the good? Not right now, because right now we have our federal GST holiday, but pretend the GST was actually being applied right now. What's GST rate? 5%. So what do you do to the cost of a good to calculate GST?
You have 0.5.
Right, but that's true. So the way you find the GST paid is let's say we're buying a $20 shirt, and we go times 0.05, that's the GST. So the GST rate here is, what's that? $1. So $1 on this. So then what's the total cost?
21.
Okay, so the total, and you can do this in 2 steps, but what I'm saying is there's no reason to calculate this separately. This is the same thing as saying 20 times 1.05. Right, this is just accounting for that adding in the whole process. So what's happening here is we're saying 3.5% is being increased, and add that to the original, which is 100%. So 100% plus the 3.5% is 1.035. Hey, welcome.
Thank you. Okay. Oh, why does it sound like someone threw up in here?
These guys came in, and I suddenly felt a little bit upset, so couldn't help myself.
So you just threw up?
Yeah, well.
And are encompassing them in pieces?
I hit it with her.
Pretty clear.
No, that'd be crazy. I love it. It does smell bad. I think it's actually like whiteboard markers mixed with someone's disgusting perfume last night.
Well, have fun with that.
Ode.
Oh, no.
It's called Ode
100% attention.
de Vomit.
Yeah, it is.
Yeah. Okay, how about this one? Number of fish in a lake is decreasing by 2%. Now, just notice something here. Decreasing by 2%. So what's 2% less than 100%? Yeah, so it's changing by 0.98. Right, multiplied by 0.98. Good so far? We're tracking? I still have no idea what you're talking about. None of those. Number of gravits is doubling. Value of the computer decreases by 1/5. So it'd be 1 minus 0.2. Right? 1/5. 1/5 is 0.2. So 1 less than 0.2 is 0.8. Ball rebounds to 3/4 of its previous height. So it was up to 4 meters. Rebounds to 3/4 of its previous height. Now it's at 3 meters. 0.75 of its previous height. So this is the converting a fraction, or converting a whole number to a decimal, converting a percent to a decimal. Good. So how about this rubber ball? Drop from the top of a 20-meter high building. Rubber ball drop, mic drop, same thing. Each time it bounces up to 80% of its previous height. Calculate the height of the ball after its 15th bounce. Now I love this setup. It's a little bit clunky, but I think this helps us a little bit. So Lucasito decides to solve the problem using a geometric sequence where T1 is 20. Okay, so this person is calling A or T1 20. So why doesn't T15? Now let's just think about the question. It's saying ball is dropped, and then it has 15 bounces. But it's saying drop is T1 in this scenario. But let's think about what actually is happening. So drop, 1, bounce, 2, 3, 4, 5, blah, 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 blah. So we get to 15. If we're calling drop 1, there's only been 14 bounces. So if A is 20, then T15 is only 14 bounce. So using Lucasito's method, what would we need to then find? If this is the setup, what would be the way to find the 15th bounce? T at what? Yeah, sure, T at 16 should do it. Yeah, fine. Try it. See if you can do it. Thank you. Problem with my beautiful students in Math 20-1 who love me so much. So, any try? No, we're waiting for you. It's the most fun when we watch you write your extremely messy writing and then complain. Okay, 16. Yep. Because T at 15 only gives us the 14th bounce if A is the drop, not the bounce. So in this setup, the way Lucasito is doing it, they're saying drop is 1, bounce 2, 3, well, but we're actually the 15th bounce, not the 14th bounce. So T at 15 would give us the 14th bounce in this case, so we're looking for one more than that. Just thinking of the scenario, and you can probably already see ahead. Nicolette is arguing that no way we should actually do it so the T15 is a 15th bounce, so we'll set it up differently. And this is part of the how you set something up makes a difference what you're solving for. So for Lucasito, T to 16 equals 20 times 0.8 to the power of, oh good, 15, n minus 1. Great. So 20 times 0.8 to the power of 15. 0.703 meters. Or could I say this in a different unit? Would there be value in that? What would be a reasonable conversion figure? Conversion, different unit, kilometers. How about that? Okay. 0.7 meters, 70 centimeters, same thing. I don't know which you like better, but I think usually with decimals we convert. So. Nice, me too. That's why I convert. Great minds think alike, right?
Yes.
Nicolette argues that the value of T15 should be the solution. So in this case, then A should be 16. Because we're saying if we want to count the 15th bounce with T to 15, then we should make A the first bounce. So the 15th bounce is the 15th bounce. So in this case, A would be 16, N would then be 15, and R would still be 0.8. But let's just see if this is the same. So t to the 15 equals 16 and 0.8 to the power of 14, right? 15 minus 1. If you're confused about how this 14 became 15, just remember in our formula it's n minus 1, so I'm just writing out 15 minus 1 as 14. We're so close to the break, Jay, I can hear it. Oh, sorry. I got a little bit ahead. I got a little excited. We already did number 2. This is that. We talked about why. So then, what about this? What about this instead? So, for each student, write an equation that represents the height of the ball after x bounces. I thought about not doing this with you, but it maybe is actually helpful. Because if the formula is, like, for what was the first name again? Lucasito. So for L and for N. The first one, it was t to the n equals 20 times 0.8 to the power of n minus 1 is the situation, right? Yeah, Lucasito, yeah. And for this one, it was t to the n equals 16 to the power of, or times 0.8 to the power of n minus 1. So how do we, but n minus 1, that's not actually the number of bounces. That's the number of, well, I guess it depends in that case. So how do we instead just say, make this scenario so that it's x bounces? What would we change there? But we want to use x as the variable here for bounces, and we don't want n minus 1 to be a variable. You should see how, this morning I thought I was going to sit here and be you guys. I was sitting in the class working through the workbook, just like you guys want to see how I wrote this. Pardon? As I said to my 10Cs often, there is an appropriate time for crying in math, but it's just always a question, what do you do afterwards, right?
Throw up the book and say, well, at least I tried.
Well, fair enough. I mean, there's nothing really profound to say here, except for that, in this case, we're asking now for what's h, so height. I'm in the middle of crying in my heart now, knowing that's how we feel. The class where everyone feels like they're being defeated while most of them are doing well.
I guess they want to stay collected. I know all of you feel the same here.
Call this one. And let's just call this one 16 to the power of. Cool. The difference is this one's accounting for the extra bounce from the first one. Have any of you guys had Mrs. Carter as a teacher?
Oh,
So she and I were talking this morning about what we call whiteboard disease. And I was saying I've had this recently. Where whiteboard disease is, you're standing in front of a board and you're talking through a equation, and then suddenly your entire ability to compute disappears. You may have seen me have that before. Let's see if we can not suffer through whiteboard disease here.
wait,
So
Mr. Boyce, how come the one is x minus 1 and the other one's x?
What's the difference between these equations, other than that?
We're not the same, like, a or
Right. So in this one, we're saying that we're starting from the 20. This one we're saying we're starting from the 16. So in this one we're counting for one less bounce.
Oh, okay.
I did this backwards, sorry. That's totally wrong. Speaking of whiteboard disease, this is the one that needs to have one less, right? It would have been on the exact opposite thing. The one that is further down is the one that needs to be three less. So let's go back up here. Let's think about our equation that it would be solved after how many bounces to get to 2 centimeters. Now just notice here there's a bit of a trick. We've changed units, centimeters. So what's 2 centimeters in terms of meters? Right. So 0.02 is equal to, now what should we do to find how many bounces? 20 times 0.8 to the power of x. And then you can try this. So at this point, we don't know how to use logs, so the best way to solve this is using your graphing calculator. Set y1, set y2. But give it a try. Okay, intersect point, what's the x value?
Mr. Where's what you get?
What did I get?
Yeah, I can tell. Ooh. Ooh.
You guys are so kind. Thank you for feeding my sugar addiction. I appreciate you guys very much. Maybe I can share if I decide to be kind, but I probably won't.
Like we're in reality TV with Dallas Craft and something. Ooh. You know you've never been there? Like in a reality TV? Yeah.
No, I've actually never been to a reality TV show. I know you guys are reality TV stars, but I just have my own YouTube channel. That's great. Okay, what did you get? What did you get? What is that? 10 point what? 10.3, something like that?
Yeah. My calculator is broken. It only gives me one line.
Is that right? What do you mean?
It only gave me one line.
They only give you one line?
Yeah.
Yeah, you just need to zoom in a lot. The y is 0.02.
Barely above the.
Yeah, exactly. Unless you're really zoomed. So can I just see what you put in? Oh, this one.
Oh, mine actually.
Oh, yeah. What's the unit? The unit here? Yeah. Well, I'm sure not done. First of all, what were we looking for? What were we looking for? So, what does x mean in this situation? Write an equation can be solved to determine the minimum number of bounces required for the rebound height to be less than 2 centimeters. So x is talking about number of bounces. So, is this 10.3 bounces? Does that even mean anything? I've just had it bounce once, twice, 3. Oh, it's 0.3 of a bounce. No. So, it's between 10 and 11. 10 bounces have happened, and it has not yet reached 2 centimeters. After the 11th bounce, it will be below 2 centimeters. So the answer in this case is that 11 bounces are needed. If I could make, any of you guys watch The Simpsons?
Mr. Boyd, mind giving me like an error like 95?
In The Simpsons, there's a character who's kind of famous for yelling at clouds and, being quite grouchy. And I feel like my old man yells at cloud moment here. This looks great.
I think my calculator is stealing my energy and it's like.
Where's your unit? Just hit enter in here. when it says no sign change, that means it's just not intersecting within the window. Yeah. Yeah, I see. I actually see that there's a few people who are getting this at 30. Yeah. Ten. That's set at 2. Yeah, and 2 centimeters. Okay, thanks. Good job, guys. Many of you there have proven an error in. This is funny. An error in our workbook, not in just my math. In this case, the 2 centimeters is 0.02 meters. You're absolutely right. Whereas this answer is based on not converted. So good job. Although this seems a little bit unrealistic that it would take 30 bounces to do that in 2 centimeters, but whatever. So what was it? X is 30.1, something like that? 30.8? 30.95. Nice job, guys. Thanks.
What did they put that we did it?
Good point, actually. Let me see how these are able to. They actually should. Oh, no, I do. Sorry, John. Because we're playing. No. So this whole no sign change thing just means your x max looks go further. You need to include the on it. Great. This one I think is the most actually useful of the problems, and this is the one that we should kind of get quickly based on what we've been doing. First of all, $5,000. Mike puts in a GIC. He gets 3% interest per year. He gets 3% added to the amount that he had at the beginning of the year. So it's not that he gets 3% on $5,000 every year. He gets $3,000 on what he had after the last year. So this is compounding interest. So the growth factor, first of all, 1.03. We got that. So let's think about his investment after 1 year. So after 1 year, he has $5,000, so his A value, I guess we'll determine what the A value is, times 1.03. Well, it says do not evaluate the product this time. Okay, feel free to if you want to. Next, write a product that represents the investment after 2 years. So you take what you had at the end of the first year, and you multiply that again by the 1.03. So you should have $5,000 times 1.03. That was after the first year, times 1.03 again. Or I suppose we could say this is $5,000 times 1.03 squared. Now let's just think about this for a second. Use this formula to write an expression that could be used to evaluate the value of the investment after 10 years. After 10 years. So let's go back to what we were talking about at the beginning of this lesson. What's the value after 1 year? After 1 year, it's this, right? And this is here after 2 years. So we're wondering what after 10 years. So what would we expect to have happened after 10 years? If this is the value after 1 year, this is the value after 2 years. Well, using this, if we're saying, okay, this is after the first year, this is like my A value. So then we would have t to the n equals A, but in this case, A is 5,000 times 1.03, because that's the value after the first year. This is a little bit strange, okay? And then what's the growth rate? Well, the growth rate is times 1.03. Right, so I've taken this whole thing as A in the first year, times my growth rate, which is the same as that part of it. And then to the power of n minus 1, so 10 minus 1, or 9. So we could call this 5,000 times 1.03 times 1.03 to the power of 9. And could I simplify that any further without actually solving? Yeah, of course. So this ends up being 5,000 times 1.03 to the power of 10. 10 minus 1, and then this is 10 minus 1, so that was to the power of 9. So this one times this one. And it's worth noticing here, in this case, that ends up meaning that in this compound interest setup, where it compounds during the first year and then every year afterwards, we're going to not have to account for that minus one. The minus one is assuming that we're not having that growth in the first year. In this case, we do. Right, the $5,000 does compound in the first year, and in the second year, and in the third year. The growth period of the first year is the whole first year. So now let's do this to the nearest cent. Well, first of all, after 1 year, how do we do this? Right, that's simple. Okay, so 5,000 times 1.03. So 5,150. Yep. After 2 years, yep, 5,000 times 1.03 squared. So that's 53.04 and 50 cents. And I just want you to think about something for a second. Here's the value of compound interest versus simple interest. So this seems really small in this case. But in the first year, how much did it grow by? It grew by 150, or 0.03. In the second year, it still grew by 3%. But what number did it grow by? Well, it grew by 154.50. It grew by slightly more than last year, because the amount that it increased by last year is also now being grown. And this happens over time. Do any of you guys watch much sports? There's been an add-on recently, a bunch on Sportsnet that's for, I think it's for Question, some investment company. But it's like this college professor with a chalkboard, and he's like, you know, the value of compound interest, and he draws this chart, and it's like, if you invested $10,000 at whatever rate, at this point, it would be here. But if you had these fees, it would be here. And that's the power of compound interest. And there's some cheesy thing, I don't remember it exactly. But it's showing that over time, the growth rate is much, much more impactful if you're able to invest. If the money is able to kind of double, that's also the stuff that's been invested in, because that part is also growing. And this, we'll see this after 10 years now. So if it had just increased by 150 per year for 10 years, how much would the value increase by? So it's 150 a year for 10 years. The value increased by $1,500, right? So it'd be 6,500. So let's see how different that is from compound. Now, 3% growth rate isn't going to be huge, but let's see what happens here. So this is going to be $5,000 times 1.03 to the power of 10 now. So this is $6,719.58. Just notice there's an extra $219, which is basically the growth of the interest. So you'll see much larger gains if the 3% growth rate is barely gaining interest. So more than that. So use this formula to calculate the value of the investment after n years. Well, we're going to simplify this to our, I guess we've already done this. Let's actually just do this with our investment of $P earning interest of I% per annum. So let's take what we've done and think through what happens here. So $P. So $P times, how would we write out the percentage, I percentage, as like a rate here? Thinking of this percentage, wouldn't the rate be 1 plus whatever our I is, if I is a percentage? So like 1 plus 0.03 or whatever, if it's growing 1 plus 0.07, whatever the I is. The way we can account for that is take your 1 and then add in the interest percentage. And then, okay, and then the amount of years, well in this case the amount of years is just straight up n. We don't have to worry about n minus 1. We've accounted for that in using our initial number as the a value rather than our number after 1 year, right? And this will be our total, we'll call that A. And this is a formula you'll see a lot of times in your future if you do more math, or if you go into business or economics, you'll see lots of compound interest. But this is the compound interest formula, and it gets used in lots of spots. Hopefully it gets used in your benefit on your investments in the future, and not just for the companies that are profiting from you on your car payments, so those kinds of things are cool. So for today, I've not quite assigned all of them. Don't need you to do 3, don't need you to do 12, but other than that, go for it. 1, 2, 4, 11, 13, 20. Well, what do you say? You guys can work for the next 25 minutes. What do you say with 5 minutes left? We make sure we're all back. And I just want to ask one question at the end. So you guys can get work time here or in that lab. Maybe we can come back together for the last 5 minutes and just do a check-in. Good? Get to it. Break! Go team, go! Who wants candy?